This is Lab 5, Falling Slinky. So, for the introduction, our purpose is to observe the motion of a falling, stretched slinky to see the effects of gravity and drag on its motion. We'll collect observation data using tracker and construct a computational model using code for gravity and drag force. Our system is the slinky, our surroundings is the floor and air, so everything else. And our fundamental principles are Newton's second law, gravitational force, and drag force. So Newton's second law is force equals mass times acceleration, and from that we can derive the position update formula and the velocity update formula. Velocity is final velocity equals initial velocity plus acceleration over time, which is the same thing as net force divided by mass times delta t. And then our position update formula is final position equals initial position plus the average of the velocities times the change in time. And then gravitational force is force equals negative mass times gravity, the gravity constant, which is 9.8. And then j hat is just showing that it's just in the vertical direction. And then drag force, air is a mixture of particles that applies upward force on falling objects. So we have to take that into account for drag force. So as you can see here, it's opposite of gravity, but it's often less than gravity, so that's why objects still are able to fall. But F drag is negative b, which is proportionality constant, velocity squared in the v hat direction. So this is our intro. We have tracker, code, and our graphs. So our initials for this, our calibration length is 1.47 meters. I use this guy's height. The mass of the slinky is 0.204 kilograms. Our initial position is very close to the origin. And then our final position, which is like around here, is that right there. And our initial velocity is 0. So this is tracker. As you can see, I calibrated down here. I'm just checking the motion of the bottom of the slinky, and then when the top hits it, then it goes to the floor. And I'll be using these values here, but minus the x values because we don't care about that, we just care about vertical motion. Okay, so then there's the code calculation. So we have our initial position up here that I put here. I used Lab 2's code for this, so that's why there's like ball and not slinky, but I put the mass, the position, and then this was our proportionality constant. That was basically just through trial and error. And we can, on the next slide, I'll show you how we know that that's right. And then so first we have time it takes for this top of the slinky to get to the bottom of the slinky. So while that's happening, the force is just gravity on the slinky, and then F net is just equal, just like that, right there. And then to do our position update and velocity update, it's from those derivations from Newton's second law. And then while time is less than 8 seconds, which is how long it took it to get to the floor, we have F equals negative mass times, so this is gravity, and then FD is our drag force, so we have negative b, magnitude of false velocity squared, and then times the normal false velocity, or norm, whatever, and then you add those together to get the force on that, and then again use the updated formulas for that part. So this is how it turned out. Right here is how we know that our b constant is right, because this is our final position in our tracker, and this is our final position for our experimental, so we know our drag force constant is right, and this is what we're going to be looking at. We have position over time of the bottom of the slinky. So we put those data together, and it is very linear. It's very much like the same. It's not exactly the same, but that is just due to center placement differences on tracker, or inaccurate drag coefficient, and then angle movement in the camera, just small errors, but for the most part that is the same. So they are the same, and so we do have drag, and we do have that the slinky, the bottom of the slinky will not fall until the top reaches it. So what does it mean? So why does the bottom of the slinky stay stationary? So the tension force of the slinky spring has an equal and opposite magnitude to the gravitational force. So the tension is pointing in the up, like the positive y direction, and gravity is in the negative y direction, and they're the exact same. They cancel each other out until the top reaches the bottom, because that's when there's no more tension force, and so now it's just gravity, and so it'll go all the way down. And then what if the Slinky was thrown down instead of dropped? And the same thing would happen, it would just happen a lot faster. So the bottom would stay stationary until the top reached it. It would just reach it a lot faster because the tension force and the gravitational force is still equal and opposite. It's just being done faster. But thank you.